Hi everybody, welcome back, and today we're talking about, in the world of logic, trying to identify a very important way of comparing two statements. In particular, when are two statements the same? And we're going to attack this problem from a few different directions. And by the end of the lesson today, we should have a good notion of when it is that two statements mean the same thing, when they are the same. Before we dive into that, or rather as a way into that, we're going to start by looking more at the conditional statement. So if you remember, the conditional statement this is the one that's like if then, and we usually denote it with an arrow. So we would say this statement reads if P then Q. All right, and we talked before in previous lessons about what is the truth table for this and a little bit about the meaning of this. But what I want to talk about is a sort of an obvious thing to do. What happens if we switch the Q and the P? And we come up with this statement, if Q, then P. Now, an important definition is simply that if this is a conditional statement, then when we switch the two parts, the antecedent and the consequent, that's what we call those, then this thing is called the converse of this one. So converse is a word you may know from out in the real world. You may not. But in this context, it has a technical meaning, which is if you have a conditional statement, and if-then, if you switch the antecedent and the consequent, then you get the converse of the original statement. Okay. And the question is, so this one is a conditional statement. This one is the converse. It also happens to be a conditional statement. And the question that we're interested in here is, do this conditional statement, if P then Q, and the converse, if Q then P, do they mean the same thing? Question mark. And here's the way that we're going to attack this question. And this is a little bit like getting into the idea of when do two statements mean the same thing. So we're going to do it first formally using just the definition, the truth table for the conditional statement and for the converse. So let's start by doing a truth table analysis. In these two statements, we want to compare this one and this one. And in these two statements, there are two basic simple statements, the P and the Q, that appear there. So we're going to include P and Q. And then we're going to include if P then Q. And then we want to compare that to if Q then P, the converse. So how do we do it? Well, as always in a truth table, we start with our basic statements, our propositional variables here, the P and the Q, and we put in all the different possible ways that they can be either true or false. So we can either have true, true, we can have true, false, we can have false, true, or we can have false, false. The idea of all of these is that if we start with some statements and we know whether they are true or false, then if we build up a more complicated statement like this one or this one, how do we tell if this one or this one is true or false based on the truth and the falseness of the original statements? And that's this whole business of truth tables, is just essentially exploring that idea. We're going to use this idea now. So first we're going to put in the truth table for if P then Q. If P then Q, let's see, if P is true and Q is true, then if P then Q is true. And you may remember that for the conditional, there's only one way to make this conditional false, And it's when the first one is true, but the second one is false. When we say if P then Q, then what we're making is something like a promise that if P is true, Q should also be true. So the only way this statement comes out false is if this is true, if P is true, and if Q is false. If the antecedent is true and the consequent is false. That's the one that happens in the next line. P is true and Q is false, and so the whole thing, if P then Q, comes out false. Now, the next line, if P is false and Q is true, if P is false, if the antecedent is false, then an if-then statement is just automatically true. It's like saying, if cows could fly, then anything. And we just take that to be a true statement because it's ridiculous. Cows can't fly. And same for the last one. If false, then false. That one comes out to be true. Whenever that first guy, the one before the arrow, is false, the whole statement is true. Okay, let's just do a similar thing over here. Let's evaluate this statement. And of course, we're going to use the same ideas here, the P and the Q, and look at all the different combinations of trues and false. The only thing that we have to worry about here is that now it is Q that is playing the role of the antecedent. It's the part that comes first. And P is the part that comes second. It's playing the role of the consequent. So let's go ahead and do it. If Q, then P. If Q is true and P is true, then the whole thing comes out true. If Q, then P, if Q is, now we're looking at this line, if Q is false and P is true, that's like saying false here for Q, but true here for P. And in an if-then statement, if the initial one, if the antecedent is false, then the whole thing comes out true. This is in contrast with the previous line when we looked at if P then Q. The next one is Q is true and P is false. And if Q is true and P is false, that means the antecedent's true, the consequent is false. And that's the only combination where we get a false. So this guy right here is going to come up false. And then lastly, when Q and P are both false, if Q then P comes out to be true. Okay. Let's now, we now have the truth tables for these. And when we ask, do they mean the same thing? What we're really thinking of is if you were to come up with a statement P and a statement Q, then would you get the same answer for this as for this, depending on that statement? And what this says is you can see two places where you don't get the same answer. You don't get the same answer here, and you don't get the same answer here. And so because of that, we would say that these two expressions, this expression and this expression, do not mean the same thing. Do they mean the same thing? Answer, no. And let's put that in red. No, and the reason why is exactly these two spots where the values in the truth table disagree with each other. Yeah. Here, if P is true and Q is false, then if P then Q gives you false, but if Q then P gives you true, they give you different answers. And that means they don't mean the same thing. Okay. Same for this one, different answers. Okay. This also suggests a way that we can determine when two expressions like this do mean the same thing. Well, when would two things mean the same thing? They would mean the same thing if the truth tables matched exactly, if they got the same answers every time. Every time this one was true, this one was true, and every time this one was false, that one was false. That doesn't happen in this case, but that's going to be an idea that we will use later in this lesson. Okay, so that's example one. Now, it's not always true that if P then Q holds and if Q then P also holds. It's not always true that they both hold. All right. However, there are some circumstances in which that does occur. So it's sometimes true. Sometimes it's the case that both if P then Q and the converse, if Q then P, hold. Now, when does this happen? let me give you an example. So if we let n be a natural number, 1, 2, 3, 4, 5, 6, 7, and we say, let's let p be the statement n is even, an even number. And let q be the statement n is divisible by 2. Now, let's just consider the two statements. If p, then q, no matter what number n is, if n is an even number, then n is divisible by 2. That is certainly the case. So this, if p, then q, that's true for every number. It's always true. Let's look at it the other way around. If q, then p. In this case, the q is n is divisible by 2. If n is divisible by 2, then n is even. Is that a true statement? It is, because being divisible by 2 means essentially the same thing as being even. Yeah, those two are equivalent. So if p, then q holds, and also if q, then p holds. In this case, we could say that p implies q, and also, so I'm going to use the symbol for and, the conjunction, which is that upside down v, and if q, then p. And what we have here is we have a statement, a conditional statement, and the converse, both being true. And this particular statement, the big one that's combined, that's the combination of these two with the and in the middle. This is a statement that's common. We end up using it a lot when we're doing mathematics, when we're doing logic, and because of that, it gets its own symbol. So we have a shorthand for this. First of all, this this statement has a name, and the name of this statement is the biconditional. Conditional because of the if-thens in there, and biconditional because those if-thens sort of go both ways, if p then q and also if q then p. And the biconditional, we have a shorthand notation for it. We just write it like this, p, and we say it if and only if q. So this is equivalent to the one above, and it's good to note that when you see this written down, this is really a shorthand for exactly this whole statement. P, if and only if q, means the following thing. It means if p, then q, and it also means if q, then p. Both. Okay. So that's the biconditional. And let's do the following. Let us find a truth table for the biconditional. So to find the truth table for the biconditional, well, what do we need? We need our initial variables, the p, and in fact, let's not do this here. Let's just go ahead and do it up above, since we've already built truth tables for the individual ones. All I'm going to do is go back up to this truth table. I'm going to extend it just a bit, and I'm going to add the biconditional here, p, if and only if q. Now, what does p, if and only if q mean? It means this, if p, then q, and a conjunction, if q, then p. Just because it might help us to remember, I'm just going to copy that and put it right above here as a reminder. So as a little reminder, p, if and only if q, this means if p, then q, and if q, then p. And in order to figure out the truth of this, what we need to do is find the truth of the first part, the first parentheses, and the truth of the second parentheses, and then take their conjunction. Now you'll notice if we have the variables p and q, this is all the combinations of p's and q's. And when we're trying to evaluate this thing, the two pieces of it, the if p then q, that appears here, and the if q then p, that one appears here. So we can fill in this truth table by simply looking at the value of this one under here, and then taking the conjunction with the value of this one. So for example, in our first row, if p and q are both true, then the if p then q is true, and if q then p is true. And it's like we're combining this one and this one with a conjunction with an and in between. True and true comes out to be true. In the next one, if p is true and q is false, well, then you have one direction if p then q is false, but the other direction if q then p is true. They have different answers, and when we take the conjunction of those two, false and true comes out to be false, because in a conjunction, you only get true at the end of your conjunction if both of the pieces, the elements, are themselves true. Similar for the next one, we have two values here. One of them is false and one of them is true, so when we take the conjunction of those, we get a false. And in the last one, well, we have a true, and when we take the conjunction of true and true, we get true. So here is our truth table for the biconditional. And of course, a truth table, you also need, in addition to this, you need the p and the q over here. So it's this, for this p and q, this gives the truth for the biconditional, p if and only if q. And I just want to make a final observation here about this if p then q, p if and only if q, this thing. You'll notice that its truth table has two rows that are true and two rows that are false. And if you look at this biconditional, at where the truth comes, those truths, the biconditional is true here when both p and q are true. The biconditional is also true down here when both p and q are false. So the truth, the biconditional p if and only if q, comes out to be true exactly when p and q agree, when they have the same meaning. Either they're both true or they're both false. This biconditional comes out false if they're different from each other. So if p is true and q is false, or if q is true and p is false. So this is sort of helps, in my brain, this kind of helps me to remember the meaning of the biconditional. The biconditional comes out true if p and q agree. And the two things agreeing is a little bit like meaning the same thing. So having the biconditional be true of two statements, p and q, it's a little bit like saying this is going to come out true when p and q have the same meaning, when they have the same truth value, say here and here. All right, that's it for this video. We're going to talk more about the biconditional and logical equivalence in the next video.